Let's take a closer look at this slide, which compares the stress-strain behavior of liquid metal to several common engineering metals. On the right of this slide, you'll see a stress-strain curve. This graph shows how different materials respond when they're pulled or stretched. Stress is on the vertical axis, which represents force per unit area, basically how much load the material could take. Strain, along the horizontal axis, measures how much the material stretches before it breaks. Now, notice the dotted blue line. That's liquid metal. Immediately you can see that it reaches a much higher stress before failure than other materials. That means it has a significantly higher ultimate tensile strength, much stronger than titanium, stainless steel, or even aluminum. Now, observe how the other metals start to curve or flatten out before they break. That's plastic deformation, where the metal permanently bends. But liquid metal's curve stays straight until it snaps. This is a defining trait of amorphous metals. They don't plastically deform. Once they've stretched past their limit, the part will crack and break at the point of highest load. This might sound like a drawback, but in precision application, it means that the part will hold its shape until the very end. Now, let's talk about elasticity. This is where liquid metal really shines. It stores a lot of elastic energy, meaning it can stretch further while still bouncing back. You'll notice how its curve keeps rising well beyond 1% strain. For context, most engineering metals deform or yield before hitting 1%. This unique elasticity is one reason liquid metal is used in applications that require precision while still being amazingly elastic. In fact, liquid metal is capable of functioning past 1.7% strain. Finally, notice the slope of the liquid metal line. It's a bit shallower compared to some others. This tells us something about its modulus of elasticity, essentially how stiff it is. While liquid metal is incredibly strong and elastic, it's also slightly more flexible in its initial response to stress compared to other high-strength alloys like 17.4 pH stainless. So, in summary, liquid metal is stronger, more elastic, and doesn't plastically deform like conventional metals. This combination makes it ideal for parts that needs to be precise, strong, and resilient while being flexible without warping. Just one more thing. If you want to learn more about liquid metal and amorphous metals, visit our website and download the Liquid Metal Design Guide. We've been told many times that it's one of the best and most useful sources on what are amorphous metals, the molding process, material properties, design criteria, and post-processing options. It's just right there. Just fill in your information and click and you'll immediately get it.